Hey guys, welcome back to the 8th video in our revision series. This time we're going to be looking at graphs. So we have a displacement graph, we have a velocity graph, we have acceleration graph, and we'll look at force and energy graphs. But about force graphs, we know that F equals to ma. So force and acceleration graphs are going to look quite similar to each other. But let's get started with our displacement graph. So I'm going to pull up a few points here that are really sort of interesting, I guess. So our first point A is where the particle starts at time t equals to 0. So at time t equals to 0 seconds, it has been displaced nowhere, which means it is actually starting at the equilibrium position. And if we look at our velocity graph, and these three graphs are all interconnected together. So our velocity graph is actually saying that it's actually moving in the positive direction. So what that essentially means is that if we had a particle, it is moving to the right, then it's moving back to the left through the equilibrium, and then back to its origin point. Okay, so this would be A, and then it moves to B. From B, it goes to C in the middle, and then it goes to D, and then it finally returns back from D to E. And we do know that it is traveling fastest as it's going through the equilibrium. So it's moving with an initial velocity of +3 meters per second. And then it is momentarily stopping. So here, if we isolate those 2 points, so the velocity and the displacement at points B, that is a really, really good match, okay? Because it's not moving, but it's at its maximum amplitude, right? So that is actually a maximum amplitude, whereas this point here is a negative amplitude. Okay, and as it falls back through, it's cutting back through equilibrium. If we look back up there, and that's correct. Okay, so that's what's going on with our velocity graphs. And now acceleration, remember acceleration and force, these are, the force is a restoration force. So it's working against the direction of things. So this is where it's really, really important to remember the negative for something like force, right? F equals to negative kx, right? So force and displacement are opposite to each other. So that's why that they both actually share the sine curve, right? So displacement is actually going up, but they are opposing each other. Okay, and likewise down here, they are also opposing each other. Okay, so that's why it's really important to draw acceleration starting off going in the opposite direction of the displacement graph. Okay, so if at any point, so let's suppose, I'm gonna have to need a little bit more paper. Let's add another sheet of paper here. Okay, so we've got a little bit of paper down there. And so suppose the displacement started off in the negative direction. So the graph that we had at first was the displacement was in the positive direction first, okay? So this was displacement. And if we used a different color for the acceleration or even the force, then it has to go opposing, but it is proportional to each other, okay? So it's really important to remember that they are always opposing each other. Okay, Last little bit of information here is about energy. We purposely used three different colors here to highlight this. So the total energy, we see a straight line, and what the straight line here means is that there is no change. So straight line indicates that there is no change in the total energy. This is obviously assuming a frictionless environment. So it's an ideal or a frictionless environment. Okay, but really, if we did have friction, then the total energy would actually essentially decay over time. So it may look something like that, in which case it'll eventually reach zero. Okay, and again, this is also in line with what we're seeing at first, okay? So kinetic energy is actually at a maximum value here. So it's starting off with a maximum value, and then it's reaching a minimum value of zero. So it's reducing to no energy, okay, or 0 joules of energy here. And that actually, it makes a lot of sense when you look at the velocity graph here. Okay, so as it reaches zero energy, that would be at time 2.5 seconds later. So if we were to synchronize the energy graph, this would be at 2.5 seconds. Okay, so right at point B, right there, 2.5 seconds later, it's reaching zero velocity. Okay, and again, if we just pull this up, EK is 1/2 mv squared, right? So when it's not moving, so when v equals to 0 meters per second, of course, we're going to get no energy as a result of that. Okay, and likewise, at the top of the graph, at our starting point, we have the highest velocity, and that also gives us our maximum starting energy. And this graph, because energy doesn't have a direction, right? Energy is not, it's a scalar quantity, meaning it has no direction. So we end up with a line going back up because it's regaining that energy on the other side, okay? It doesn't follow like, okay, I'm gonna go down essentially to have no energy, all right? It can't follow that because that doesn't make sense. You can't have negative energy here, which is what you're really saying here, right? So that's why it looks the way it does, okay? It forms sort of this, I guess, two arcs that are inverted on each other, okay? All right, I think there is a revision question here. So if this were a displacement graph, we're asked to sketch the velocity, acceleration, and the kinetic energy of this graph. Okay, so this is displacement, x. So it's actually starting off, if we maybe gave it some time interval. So let's say here it was 1 second later. Here it was 2 seconds later. Here it was 3 seconds later. And there it is 4 seconds later. So that we're assuming is at 0 seconds. Okay, so if we cut that up, then what we're essentially saying is that it's starting off at a maximum displacement, so a positive amplitude, and it's heading back to the equilibrium position, okay? So the velocity graph is going to look, it's at a maximum, okay? So that's gonna have 0, it's gonna start there for sure. It's heading down. So velocity is heading into the negative direction to start. Right, it's displacing back towards the middle, so it's displacing in the negative direction. So velocity is going to follow there. So that would be at 1 seconds. Okay, and then it's reaching the other maximum, at 2 seconds. So that's when it's not moving. 3 seconds later, and 4 seconds later. Okay, and so let me just have a quick little double check for that time and velocity. So one thing that you will sort of notice here that maybe I forgot to mention is velocity is always, this would be a quarter of a period later compared to displacement. And if we look at that comparison here, this has been delayed by a quarter of a period, and that's actually right, okay? So this is, sorry, no, 2. That's essentially half a period. Sorry, a quarter, it's a quarter of a period. Pi by 2 is a quarter of a period, yep. So pi by 2 is a quarter of a period. And yeah, that's right. Okay, so it's delayed by pi by 2, so that's why it's starting off down there. Okay, that looks good. Okay, acceleration graph. So we just spent quite a bit of time talking about this. Is acceleration graph is always going to oppose the other one. Okay, so the acceleration graph, if this was displacement, so that was displacement, then acceleration will always oppose it, like that. Okay? And lastly, kinetic energy. So if it was starting off at a maximum displacement, that means it has no energy. So it's starting off with no energy, and then it's reaching a maximum energy going back down. And if it was actually for over the entire 3-second duration, it would be 1 second, 2 seconds, and then it would go back up, back down again. So it'd be 3 seconds, 4 seconds there. Okay, so each time it does drop back to 0 joules of energy once it reaches its maximum points, 0 joules. Okay, thanks for watching.